Hey everybody, welcome back. So today we're going to be talking about complex numbers, or actually defining them. So remember last time we did a very brief recap of Calc 3, but again, that was a very quick review. It's not necessarily covering everything we need to know, but it should get us started on our journey here through complex land. So today what we're going to be doing is defining the complex numbers themselves. So the number system that we're going to be working with the entire semester, which you hopefully are all somewhat familiar with. So we're going to be giving some new presentations today that you might not be familiar with, but at least at its heart, hopefully everyone remembers at least the complex number I, for instance. So before we jump into that, just to give you sort of a quick overview of chapter 1 and what we're going to be doing. So remember at the end of last video, we talked about polar coordinates, which was a new way of representing R2. And again, the reason why we like that representation is it helped us with integration, at least back in Calc 3 it did. Now with complex numbers, we can actually view them in quite a number of ways. In fact, we're going to talk about 4 ways, not in this video, but at least over the course of the next couple of videos on how to actually think about complex numbers. And you want to use each representation sort of to your benefit. We usually switch representations depending on the context or the problem we're looking at. So you're going to want to be comfortable with all of them, but just be aware that there are 4 different ways, at least in this class, that we're going to be viewing complex numbers. And then at the end of the chapter, I should say, we're going to be talking about what's called topology of the complex plane. And topology is something for you that are going on to graduate school you'll be studying for sure. But topology is sort of the study of geometric objects and their structure, and it's a really awesome branch of mathematics, to be completely fair. But let's go ahead and get started. So like I said earlier, hopefully you guys remember at least one complex number I. Okay. And usually what people remember is that I is the number for which I squared is equal to -1. Okay. Or said differently, it's the solution, or it's the root of the polynomial x squared plus 1. Or it's a solution to this equation here. Now, funnily enough, complex numbers actually didn't originate with what we would call quadratic equations or quadratic polynomials. They actually started with cubic polynomials. So the person that's credited with defining complex numbers is this Girolamo Cardano, but he was actually studying cubic polynomials, so something like this. Okay, and really complex numbers came out of this idea that I want to have a number system that has the roots of all these polynomials. Okay, so his quest was, I want roots. And by roots, I just mean solutions to a cubic equation in this case. And so the complex numbers you can really think of are a way of creating a number system that actually has roots for all the polynomials that we can think of. And we'll see that at the end of this video today. But that's where complex numbers got started. They got started with trying to find solutions to things like this. And so we needed to define another number system that actually contained those solutions. And that's sort of the complex numbers in a nutshell. They're sort of amazing in that way. Anyway, let's go ahead and get started. Enough history. Okay. So this is going to be probably different than you're used to, but this is the first way we're going to think about complex numbers. So we're going to think about them as points in 2-dimensional space. Now I'm saying R2 here. I don't actually mean the complex numbers are R2, but I want you to take away from this that we're thinking about complex numbers as living in a 2-dimensional plane. Which is kind of a mouthful, which is why I didn't actually put that on that slide right there. Okay, so the complex numbers can be defined in the following way. So C, okay, so that's going to be our notation for the complex numbers, is the set of tuples x comma y for which our first and second coordinate belong to the real numbers. Okay, so again, the complex numbers, the first way we're thinking about them, they're tuples of real numbers. Okay, they're points, x comma y. So given this structure, we can define the following addition and multiplication. So meaning we can add and multiply complex numbers through the following action. So addition, super nice. Okay. So to add 2 complex numbers in this representation, you just add component-wise. Component-wise. which again should remind you of our last video. Remember with vectors, how do you add vectors in R2? You just add the components. It's the same idea with complex numbers. You just add component-wise. Now multiplication, on the other hand, I'm actually going to pick out a different color for this one, is a little bit more funky. Okay, so we define multiplication in the following way. So xy times ab is equal to xa minus yb. So xa minus, so xa minus yb, comma, and then we do xb plus ya. Okay, so it's kind of like a weird foiling. Now we'll see why we're defining multiplication like this in this strange way when we talk about our other representations, but this is how we're multiplying complex numbers in tuple form here. So it's like a strange FOIL. And by FOIL, I mean, you know, the algebra FOIL that we had back in, I don't know, algebra class, long time ago. Okay. So the complex numbers, at least if we define it this way, they form what's called a field, which this is kind of beyond the scope of this class, I should say. But the idea is that we have all the nice properties that we would ever want with the complex numbers. Okay, so that's what I want you to take. A field in mathematics is just really, it's a number system that has two operations. Usually we think about it as a multiplication and an addition, but we have sort of the properties that we normally take for granted. Okay, but in any case, C is what we call a field, meaning, and I'm going to sort of go through these one by one. So the first property here is closure. If I add two complex numbers, I get another complex number. Okay, so for those of you that are coming out of Foundations in Mathematics, this is one of our favorite results, at least in terms of complex numbers, not integers. The second property here is associativity, so or associativity of addition, I should say. Third property is commutativity. Okay, so it doesn't matter what order you add complex numbers. 1.7 here is if you add 0, the 0 vector, you just get itself. So it's like if I take 1 and add 0 to it, I still get 1 back. Okay. 1.9 here is a distributive property. Okay, so if I'm multiplying xy times, or into, I should say a sum, then we distribute over that sum. 1.10, this is closure under multiplication. Okay, meaning if I multiply two complex numbers, I'm still a complex number. 1.11 is associativity with multiplication. 1.12 is commutativity with multiplication, meaning again, similar to addition, it doesn't matter what order you multiply complex numbers, you'll still get the same thing in the end. 1.3, this sort of seems maybe fairly obvious, but it's actually sort of tying together a pretty cool thing that we'll explore in a little bit. But if you take xy and multiply it by 1, 0, you get xy back. So this is like saying that if you multiply 5 times 1, you get 1 back, or I'm sorry, you get 5 back. Okay. When you guys get into abstract algebra, we're saying that 1 is what's called the identity. And then lastly, for all complex numbers that aren't 0, if you take x, y, and you dot it, or you multiply it with x over x squared plus y squared, minus y over x squared plus y squared, you get 1, 0. Okay. Now this might seem strange, but this is almost like a normalizing thing that we have seen back in Calc 3. So this isn't something completely new, although it looks kind of bonkers. But in any case, these are the properties of the complex numbers. Again, it's a number system that sort of has all the properties that we love. Now I do want to note you should be able to prove all of these. We're actually going to prove today, just to show you how to prove one of them. We'll prove 1.13. Next slide, please. There we go. Okay. So what we want to prove is that 1.13, which said that if we take xy and multiply it by 1, 0, we actually get xy back. So this is what I would call, or what we would call in abstract algebra, the identity property. Okay, so recall, so proof. Okay, we need to remember we have a backwards multiplication or a strange FOIL. So using definition of multiplication, we have that xy dot 1, 0 is equal to, oops, 1 second, I'm trying to, my screen just totally blanked. There we go. Okay. So in any case, remember we have that strange FOIL, right? So we have, for the first coordinate, x times a minus y times b. So x times 1 minus y times 0, comma, get a different color in here. We have x times b plus y times a. Okay. So again, that's using our strange multiplication there. Okay, so this line here was coming from our strange multiplication rule. Okay, so if we simplify this, we're going to get x minus 0, comma 0 plus y, which does give us x comma y. Okay. So again, what this proposition is saying is if you take any complex number and multiply it by 1 comma 0, you're just going to get your complex number back. So again, the way to think about this, it's like taking any number, let's say 25, and if you multiply that by 1, you get 25 back. All right, so what we just saw was that our complex numbers have really, really nice properties that we're going to be using all the time, but properties that we've sort of come to know and love just by our experience with mathematics thus far. So meaning complex numbers, we can multiply them, we can add them, and we get really, really nice properties with that. Now we also get two other following facts, which I recommend stop the video and try to prove on your own. You should be able to prove these just using our strange multiplication. But this is going to allow us to view the complex numbers in our second representation. So I'm going to call this number 1 and this number 2. Okay. Now using number 2 here, we actually can break up any complex number in the following way. Okay. So given any complex number x comma y, I can always break this up. Now this is just using straight up vector addition, nothing too complicated here. X comma 0 plus 0 comma y. Okay, so nothing too strange about that. In fact, what we can also do is write this, or at least our first component here, we can write this as x comma 0 times 1 comma 0. Okay, that is using number 2 there. Okay, now the tricky part is the second coordinate here. Okay, so using 2 in this way, so we're thinking about this first coordinate here as, well, y comma 0 times 0 comma 1, I should say. Okay, so if we use property 2 with these 2 points here, we can actually write our second coordinate as follows. Now notice this is going to be really, really subtle. But this is equal to, so how can I use equation 2 here to rewrite 0 comma y? I can rewrite it as y comma 0 times 0 comma 1. Okay. Now it doesn't look like I did much there, but notice I flipped. Essentially, we flipped the second coordinate into the first coordinate there, but it sort of came at a cost of 0 comma 1. Okay. So what this is telling us is that we can write x comma y as a linear combination of 1 comma 0 and 0 comma 1. For those of you that know linear algebra, this is what we're getting at the idea of a basis or basis vectors. But the other thing I want to note too, 0 comma 1, remember, has this strange property, right? If you take 0 comma 1 and you multiply it by itself, you actually get negative 1 comma 0. Okay, and 1 comma 0, like we said before, you can kind of think about this as the number 1. Okay, but for 0 comma 1, we can't think about that as the number 1, but we can think about it as another number. But just keep in mind, what is that number? Think about property 1. What's a number that you know if you square it, you get a negative 1? And the answer is I there. So we can sort of think about this as our imaginary number I there. Okay, so using this fact, we can think about the complex numbers as the following. We can think about C as the set of x plus iy, and here let me just write for you so you see where this is coming from. Remember, we had our last equation was x comma 0 times 1 comma 0 plus y comma 0 times 0 comma 1. So that's what we ended up with. Okay, so I can think about complex numbers as x, okay, times 1, which is what we have here, plus y times I, which is what we have here. By the way, I didn't mean to put a little, forget what that dot means, but it's not what I meant to put there. So here's another presentation of the complex numbers. So instead of thinking about them as tuples, x comma y's, we can write them as sort of mathematical expressions or just regular numbers, x plus I, y. Okay. So again, this is our second presentation. And again, this is coming from the fact that we can write any complex number in this way here. So x times 1 plus y times, we're thinking about 0, 1, since it has that strange property. We're thinking about that as the imaginary number I. So we get this second presentation here. Okay. Now with this presentation, we actually have sort of a different way of thinking about the parts of that presentation. So if you're given a complex number x plus iy, okay, so using our second presentation there, we think about this first part as the real part. Okay, so x would be the real part of this complex number. And then y we think about as the imaginary part. Okay, and we denote that with re, so that's the real part, and im for imaginary part. Okay, now the reason why we think about it this way, this gives us another connection back to our R2 presentation. So we can think about the complex plane as an x and a y axis, where the x-axis is our real part and the y-axis is our imaginary part. So for instance, if I'm thinking about the complex number, I don't know, 3 plus 4i, okay, that would be 3 along the real axis, 4 along the imaginary axis, and boom, right there. Okay. If I was thinking about just the complex number I, okay, that would be at the point 0 comma 1. Because I is equal to 0 plus I, right? Okay. So we can think about, again, complex numbers in two ways, as points in R2, okay, or as, for lack of a better term, regular old numbers, x plus I, y, but there still is this connection though, okay? So the x part is what we call the real part, the y part is what we call the imaginary part, and this gives us a connection on how to graph. If we think about the y-axis as the imaginary axis, and the x-axis is the real axis, then we can take a complex number in quote-unquote regular old form here and convert it into a nice R2 point, or tuple. Now before we get to the end of the video, I want to explain, remember how we have that funky multiplication, right? Remember we defined xy times ab in that sort of funky way, where it was x times a minus y times b, comma, xb plus ya. Okay. Now the reason why we defined it in this way is really related to, or at least I think it's easy to see why we would want this in terms of our second representation. So let's say we were multiplying the complex numbers x plus iy times a plus ib. Okay. And we're going to see exactly why our multiplication, we're defining it in sort of this strange way by foiling. So let's go ahead and FOIL this out. What do we get? So we get XA times, now remember, I squared is -1, so we're going to get minus YB, okay, plus IXB plus IYA. And if I factor out I, what do we get? We get XB plus YA. So does this look familiar to you? So this is why we have that strange multiplication, which I think is really, really evident when we think about multiplying complex numbers in this representation here. So up to this point, we have two representations of the complex numbers. We have x comma y, so we're thinking about them as points in a two-dimensional plane, or, and again, for lack of a better word, regular old points, x plus iy. Okay, where x is what we call the real part, y is called the imaginary part. Now, before we get into other representations, and we're actually going to end this video really quick, I wanted to bring up the fundamental theorem of algebra. Okay, so again, remember what I said in the beginning of this video, complex numbers were sort of a way of solving polynomials, or solving for roots of polynomials, I should say, or be more precise about. So that's summarized in the following theorem. So the fundamental theorem of algebra says the following, which we're not going to see a proof for until chapter 5, by the way, but the fundamental theorem of algebra says the following. Every non-constant polynomial of degree d has d roots, counting multiplicity in C. Now, if you're like, what the heck's multiplicity? This is a pre-calculus thing. But remember, multiplicity is just how many times is something a root. So for instance, if we're looking at the polynomial x plus 1 squared, okay, we have that x, or -1 is a root, but it's a root with multiplicity too. Meaning it's a root, you can think about it, it's a root 2 times because of this power right here. Okay, so that's what it means, multiplicity. But the fundamental theorem of algebra more generally is saying that if you give me any polynomial of degree d, so let's say a sub d x to the d plus yada yada yada, a1x plus a naught. So give me any polynomial of degree d, we know that the complex numbers contain all the roots of that polynomial. Okay. And again, that's sort of the purpose of complex numbers, at least initially, was that they're this number system that contains the roots of any polynomial we can think about, which is kind of insane, but also super, super awesome though. But that's sort of the motivation behind them. Mathematicians were really trying to solve polynomials, or find, I should say, let me be more precise, they were trying to find the zeros of polynomials. But like we see really quickly with, for instance, x squared plus 1 equal to 0, the real numbers don't actually have all the roots, right? For instance, there's no real number that satisfies x squared plus 1 equals 0, right? Because you're putting a negative in a square root. But the complex numbers are a way to fix this in a way. Okay, and they're giving us all the roots of any polynomial that you can think of. Oh, that's really cool. Anyway, all right, I will see you guys in the next video.